We begin lecture 29. Today we will bring to a closure or conclusion our discussion on the Whiteson stationary uncorrelated scattering models. I hope you've had a chance to sort of put the pieces together and see how each of them adds value. The classification of channels was something that we had discussed in the last class. We'll briefly review that. But before that, this picture is something that you will find in a lot of the classical books, Proekis, on Haken, in Molish, Goldsmith, all of them will give you this picture because this is the starting point for us to completely capture the Whiteson stationary uncorrelated scattering model. So starting with the time varying impulse response, you compute the autocorrelation function, and then it's two transforms, and then the interpretations that come from there. These are the reference points I would like you to look at and make sure that you are comfortable with that. The two parameters that are very useful for us is one is coherence time, other one is the coherence bandwidth. Coherence time tells you how frequently you should estimate the channel, or for what duration of time you can assume that the channel is more or less constant, and coherence bandwidth is the bandwidth over which the frequency response of the channel is correlated. And if you want to do frequency hopping, you want to make sure that your frequency hops are greater than coherence bandwidth, and your time channel estimates are done at a time period which is less than coherence time. So basically you make sure that you are estimating the channel as it changes. Okay, the pictorial representation helps us also greatly. This is the time domain autocorrelation function. We showed that it's a stationary function. Its Fourier transform is a Doppler spectrum bounded by plus minus maximum Doppler frequency. The same autocorrelation function, if you set delta t to be 0, you find that we now have a power delay profile which can be characterized, which can tell you the behavior of the time domain or the dispersiveness, dispersive behavior of the channel, which then leads us to a transform which tells us what the coherence bandwidth is. Using this the two parameters, the coherence time and coherence bandwidth, we did a 4-quadrant classification of channels. We tried to define when is a channel considered wideband, when is it considered narrowband. Again, a lot of it depends on the coherence bandwidth, and the coherence bandwidth in turn depends on the dispersiveness of the channel. So again, the same signal, GSM signal, can be treated as may seem to be a wideband signal under some channel conditions, may seem like a narrowband signal under some others. The symbol duration with respect to the coherence time tells us whether your channel is slow fading or fast fading, and based on this characterization we find that most of our systems of interest are on the west side of this partition, and the systems most likely to be encountered are in the northwest quadrant, which says that we are looking at frequency selective but slow fading channels. So equalizers are needed, but these are channels which we can do channel tracking and then build efficient coherent receivers. So the multiplicative fading, you have to do convolution in frequency, whereas the dispersiveness of the channel results in a convolution operation in the time domain, which means that it's a multiplication in the frequency domain. So if it is a narrowband signal, the dispersiveness of the channel is much less than the duration of a symbol, slight distortion of the transmitted symbol, and therefore the spectrum more or less is transmitted without much change. So these are the flat fading type of scenarios where it is easy for us to build the receivers. On the other hand, wideband signals, the channel dispersiveness is much longer than the duration of a symbol, which means that the symbol gets extended and distorted, and successive symbols will overlap, causing you intersymbol interference. This can be represented in the frequency domain as a spectrum of the input signal plus a frequency selective behavior of the channel, which distorts the frequency spectrum. Okay? So quick question, what is the job of an equalizer? What is the job of an equalizer? So equalizer has to basically restore this. So after, let me use a different color. So if I pass this signal, this converged signal through an equalizer, so through an equalizer, if I pass it through an equalizer, I want to get back something that looks like this. Frequency domain, I must do the inverse so that I get back my received spectrum. Okay? So the job of an equalizer is to restore the or undo the distortion introduced by the channel, either in the time domain or in the frequency domain. This is how we study in digital communications. The only difference in a wireless channel is that this distortion keeps changing as a function of time. So your equalizer also has to keep changing because it has to adapt to the distortion and undo the distortion at every stage. So that's a very good summary of the different channels that we have encountered so far. So from a practical standpoint, I'm sure that when you get a chance, you will read Molish chapters Appendix 7C. Molish Appendix 7C. Okay, and it has got two sets of channel models. It has got the ITU-R, which gives us several channels. Indoor, there is a channel A, and then there is a channel B, and then you have pedestrian, you have channel A, B, and you have vehicular channel AB, and actually there are several variants of this, but the key things that you are looking for is the tap number, that's column number 1, tap number. Second is the delay of the tap number. Third is the power that is present, power delay profile that will tell you how much of that. And the fourth one, which I want you to think about, is the spectrum, Doppler spectrum. Okay. So far the only Doppler spectrum that we have studied is the Doppler spectrum corresponding to a Rayleigh. So basically this is the Doppler spectrum that we have studied. So today we will see how this is going to play a part in it, but the different channel models that are present sometimes specify a spectrum that you should use for that particular tap. So for example, tap 0 may be specified as a Rayleigh distribution. Okay, Rayleigh distribution, is this correct? Rayleigh distribution, is that correct? This is the line of sight component. This is the line of sight component. It's like a constant that is always present, and this is the Doppler spectrum for the Rayleigh component. Okay, so basically we need to keep in mind that we are able to interpret the spectra that is given to us. Rayleigh component, it can be at 0, it can be at DC, it can also be at some specified Doppler frequency as well. So you can see sometimes they will specify that the Rayleigh is at 0.7 of FD max or FD. Okay, so some of those you can see are given to you. Now there is a spectrum called the Gauss spectrum. This is, by the way, this is called the classic spectrum. Okay, that's also known as the Jake spectrum. There is a Gauss one which has the following behavior. This is minus FD max or minus FD. This is FD. It has this type of a response. Can you interpret this for me? What is this power spectrum telling you? There is a strong component near minus FD and a not so medium strength component, but it is not all frequencies are not present. There are some dominant paths that are present. So these are slightly different environments from that. So this is called Gauss 1. Gauss 1. There is a Gauss 2, which is a complement of that. It's got a small component in the negative side, strong component on the positive side. Again, it's the complement of that. So some of the taps may have classic, Some of them may have line of sight, some of them may have Gauss 1, some of them may have Gauss 2. You have to implement them appropriately. Okay? But how does the underlying process work? We basically, this is the power spectrum, RH of tau. Ignore this notation. We have been using RH of tau versus tau. You have a power delay profile that is present. You set a threshold. This is the threshold. Anything below this, we are not interested. So if the channel goes below the threshold and remains below the threshold, then that's the point at which we declare that the channel response has ended. But as long as there is another portion of the power delay profile, supposing this were to come up again, sometimes it can happen. So which means that you have to take into account this portion as well. So anything that's above the threshold, you have to take into account. You sample it based on your time resolution, and then you can then call this as tap number 0, 1, 2, 3, and so on. That's how the channels are presented. So sometimes they will say that, okay, the first 4 taps are classic. That means it corresponds to the Jake spectrum. Then they can call this as Rayleigh, then this as Gauss 1. So that's how ITU models are specified, the cost 207. So please do read and make sure that you are comfortable with the explanations given and what it means. So basically you have taken a power delay profile, you have sampled it, you have gotten the distribution of the power. If you did not specify anything, then your interpretation is that it has to be the classic spectrum. Okay, default is classic. That means no line of sight. There is Rayleigh statistics on each of those taps, and the fading is independent is usually the assumption that is made. But if they specify one of the other modes or the spectra, then we have to appropriately account for that in our simulation. Okay, any questions? So that pretty much summarizes the complete landscape of wide-sense stationary uncorrelated scattering models, how to interpret them, how to characterize them, and how to implement them. But now we will get into the computer's implementation of that. But this framework is very important for us to do the implementation. Any questions? Okay, so then we go back to asking the question that where we ended in the last part of the last lecture. So if I were to want to generate a fading channel, ZR of n plus j times Zi of n, I need to generate a sequence of independent complex Gaussian random variables. Now that's what this process will generate for me. But I know that I must have, in the time domain, there is a autocorrelation RH of delta t. I must get some P naught times J naught 2 pi FD delta t. I cannot get independent samples from instant to instant. So this is not allowed. This is independent from time instant, time instant. What I need is this type of, but how do I force my Gaussian noise to have that time correlation? Okay. So this is where signal processing helps us. Correlation in time corresponds to coloration in frequency, because if I have a autocorrelation which is an impulse response, that means there is no correlation. In the frequency domain, it is flat. So if I have a correlation that has got some time domain behavior, then I would see some coloration in the spectral domain. So that is what and this correlation in the time domain has to be a Bessel function. So which says that either I can somehow try to include a Bessel correlation into my white noise generator. An easier thing would be is to generate the white noise, pass it through a filter which has got a spectrum that has this shape, and you're guaranteed that your output signal has the appropriate correlation because you have taken care of it in the frequency domain. Okay, by the way, what you need to take into account that the frequency response of this filter H Doppler of f should be square root of S of f, right? Is that the notation that we have used? No, S of rho. Okay, yeah. So whatever is so basically the square root of the power spectrum is what you should get, because when you take the output power spectrum, it will be input power spectrum multiplied by the power spectrum of the filter that you have used, which will give you the Doppler spectrum. Okay, it's the square of the power spectrum of the filter. So this is the way we would generate. So obviously we need to introduce a filter here, and these filters are the Doppler filters. I'll just write it as HD. Okay, so we can write it as HD of n. If you think of it as a sampled sequence impulse response, and the same filter has to be used here also, because both the real and imaginary parts have to have the corresponding spectrum, and then you combine them as real and imaginary, which are independent of each other, and together we will get the desired result, desired behavior in our result. Okay, so the process of generating the desired response is as follows. My method is to generate white noise, pass it through a filter, and then obtain the output. So the first method that we will be studying is called the Clark and Gans method. Clark and Gans method, again refer to Rappaport for a good discussion, but we will cover the key elements in our discussion today. So basically what we are going to do is take white Gaussian noise, white Gaussian random variable. White basically means it's uncorrelated from time instant to time instant. Pass it through a appropriate filter, H Doppler of n, and this would be the real part, and correspondingly obtain the imaginary part, and we get ZR of n plus j times Zi of n. Okay, that's the Clark and Gans model. Okay, now I want you to think of the following aspects of the filter. By the way, this will guarantee for us that the following property will hold. RH of delta t comma tau is such that whatever is generated should satisfy expected value of HD of delta t comma tau HD star, this is t comma tau, this is t plus delta t comma tau. Okay, this has to be the Bessel function that we are interested in. Now the continuous time is the basis, but actually what we implement will be a discretized version of it. So don't get confused. Why am I writing n here? This is the discrete implementation. The underlying process is the continuous time process. You can also write it in the following form, just for clarity. If this is m comma tau, this can be written as HD of n tau h star d n plus m comma tau. Okay, so basically there is a discrete equivalent of it, but you think of it as a continuous time process which is filtered, and then we sample it. Then all the properties that we are interested in are available for us in a clear fashion. Okay, first observation that I want you to make is, can you tell me something about this filter? What can you tell me about the impulse response of this filter? Real, that's correct. Very good. Anything else? It's a very sharp filter. Look at how steep it falls, basically. So when you have very sharp filters, what is your impulse response behavior? It will be very long. Okay, so which means that in order to generate a reasonable sampling or representation of the signal, you're going to have to filter a lot of data before you can get a usable segment of information. So the first observation is that the long impulse response. So please write it down with the correct interpretation and explanations. I'm going to just write down long impulse response which means that you're going to have the filtering process is going to be cumbersome, and therefore long impulse response is a problem for us. Okay? And the reason it's a problem for us is because this will involve, this process is a convolution in time, and convolution will require a lot of data, and because the impulse response is very long, you would appreciate the fact that that means there's a transient that is present with the output process. So you have to wait for the usable portion of the signal. So that is again a challenge. Another observation that is very important for us, this is minus FD to FD. Okay. Now I want you to get a feel for what type of a filter this is. Basically it looks like a low pass filter, it's a little bit of a non-uniform filter, but it is it passes the low frequencies. But what is very important is that what is the bandwidth of the filter compared to your sampling frequency. Okay. So let's take an example, because that's usually how we can appreciate the order of magnitude. Let us say that the Doppler frequency is 100 hertz. Doppler frequency is 100 hertz. Now we will take a system, communication system, which has the following symbol rate: 24.3 kilosymbols per second. This happens to be one of the 2G systems. 24.3 kilosymbols per second. Okay, so which leads to a symbol duration T symbol of 41.2 microseconds. And as you are familiar with from the computer implementation, most of the time our receivers will do 8x oversampling. So my sampling period, T sampling, is T symbol divided by 8, because that's I'm doing 8 samples per symbol, and 1 by T sampling frequency is F sampling. That's my sampling frequency. That corresponds to 194,400 hertz. So 194 kilohertz. Okay. So that means if I were to show it on a digital scale, pi would be 1/2 of the sampling frequency, is quite far away. This is 100 hertz. The 1/2 of the sampling frequency is 97,200. Did I get that right? Yeah. So basically this is a very, very narrow filter, okay? And it has got its own set of challenges, as we will see in a moment. But the important point to know is this is how Clark and Gans proposed, and this was how it was implemented and used for quite a good period of time. It was used before another method was proposed that was called the Smith method. The Smith method was a way of saying, okay, I think this is very complicated, because first of all you have to generate a long impulse response and you have to filter a lot of data, and also keep in mind that for each FD it corresponds to a different filter, right? You have to basically generate depending on what Doppler you want to different filter. What I mean by different filter is a different impulse response. So it's not a fixed or a standard. You cannot pre-compute all of the Doppler frequencies that you want, because your Doppler frequency changes based on your environment. So there are some limitations of this filter. So Smith method basically said, this is the best way to do it. We don't know of any other way of doing it. Can we do it more efficiently? So basically the Smith method came along and said, here is what we are trying to do. So if this is, we call this as XR of n, this as HD of n. What we are trying to do is XR of n convolved with HR of n. That's what we are interested in. So this can be written as the inverse FFT of XR of n multiplied by FFT of HR of n. I think this is what we already discussed before the start of the lecture. Convolution in time can be implemented using the following frequency domain operation. Now this is where the other question leads to. Now what are XR of n? they are a sequence of uncorrelated Gaussian random variables. So if I take a linear transformation, the FFT of that, then what comes out is another set of Gaussian random variables. So the important point to note is that I don't need to do this. I can generate this directly in the frequency domain. Frequency domain Gaussian random variables can be generated. However, we need to keep in track one important element. Gaussian random variables can be done, and that important observation is as follows. So because XR of n is real, the Fourier transform is going to be conjugate symmetric. XR of k basically will have conjugate symmetry. Conjugate symmetry. Okay. So now instead of doing XR of n and then taking the Fourier transform, we are going to generate Gaussian random variables already in the frequency domain, and the way we would do that is as follows. So you would generate XR of 0, then you would generate XR of 1 and XR of n minus 1. They are not independent of each other. These two are complex conjugates. This is nothing but XR conjugate of 1. Okay. XR of 0 is a real valued random variable. XR of 1 is a complex number. Its conjugate must be at the last. Similarly, XR of 2 and XR of n minus 2 are also related. So basically you must ensure conjugate symmetry is present, so that when you do the inverse Fourier transform you will get a real sequence. And but apart from this, this is very simple. You just generate directly the Gaussian complex Gaussian random. So the Smith method says generate complex Gaussian random variables in the frequency domain. Okay. In frequency domain, what should you do for the filtering process? Very straightforward. Sample it. You get this as your sequence. Multiply the FFT of 1, and there are lots of zeros. Remember, because this is there are lots of zeros present in the system in your Fourier transform of your filter. So lots of zeros, they will multiply, they will remove out, and then take the inverse Fourier transform, and then get the XR, the output that we are interested in. Okay, so I hope you are familiar enough with the how to do linear convolution using FFTs. And the Smith method basically said that we will do the convolution in the frequency domain with the added observation that the complex Gaussian random variables can be generated directly in the frequency domain, and you don't have to do the transformations. Okay. Now the important aspect that we observe, what are the limitations? Here is where the problem will come, and I hope you will be able to appreciate this aspect of it. Okay. So go back to our example. Doppler frequency 100 Hertz. Doppler frequency 100 Hertz. Now let us say that we want to have a certain resolution of our of the FFT process. So let us say we assume that we want this condition. We want at least 21 samples in the range minus 100 to 100, in the range minus 100 Hertz to 100 Hertz. That means your number of samples, so this is 0 up to 10 on either side, okay, minus 10 to plus 10. So 21 samples are present at least. Why? Because only then I will get some resolution of my, because all the shaping is being done by these samples. And keep in mind that there's a lot of zeros that are present in your filter Fourier transform. So I want to do this so that I can get good capture the Doppler spectrum in an accurate manner. Okay. So this tells me that my delta f, That means the spacing between my FFT samples, in the FFT coefficients, has to be 10 hertz. Correct? Basically, only if I have a spacing of 10 hertz, I will get this type of resolution. Now, what is the size of the FFT? That's very important. Now, the size of the FFT depends on your sampling frequency. And we already said that the sampling frequency is 194 kilohertz, 194400. So, the size of the FFT is 194400 divided by 10, which implies if you want to take a power of 2, it would have to be 2 to the power of 15, would be basically that would be the size of the FFT. No problem. This corresponds to, at this sampling rate, it corresponds to approximately 169 milliseconds. So, one set of data that you will generate corresponds to the fading pattern at 100 kilohertz of 169 milliseconds. No problem. This is the Smith method, and we said, okay, we have done it very efficiently, and therefore we are in good shape. Now, supposing I change the problem on you, and I say that the maximum Doppler is 10 hertz. What is your delta F? Delta F becomes 1 hertz. So, what is your FFT size? It's now 10 times, basically it's 10 times larger. So, the size of the FFT now will become 2 power 18. That's the one that will satisfy the number, and this will generate for you 1350 milliseconds of data. Okay? Now, you may still not see that there is a problem, or may still wonder, why is there a problem? In one case I generated 169 milliseconds, another case same set of data. I'm still interested, but I just changed the Doppler frequency. You told me size of the FFT has to change. Now the sequence has changed. Now the problem comes from the following reason, because if I tell you that my environment is such that I am hopping every 1 millisecond. Okay. So, what am I expecting from you? A fading pattern that lasts 1 millisecond, and then the next millisecond, because of hopping, it's a different channel altogether. The next 1 millisecond. I'm telling you, I want to simulate a frequency hop system. What will you tell me? Sorry, I'll give you 1,350 milliseconds of this thing. You throw away 1,349 milliseconds and keep 1 millisecond. So, you see that you're basically there is a lot of wastage in our computation that we are doing. So, the question that we ask is, yes, many times we want to have a fading that is of this type, right? 1 millisecond duration, correlated fading. Then I do a hop, therefore another 1 millisecond of correlated fading. So, like that you want to generate. The question that we ask is there a better method? If I want 1 millisecond, I generate 1 millisecond, not 1000 milliseconds and throw away 999 milliseconds. So, is there a better method? And that method was actually discovered and proposed by William Jakes, and therefore has been known as the Jakes method, which is the heart of what we will be doing in today's lecture. Okay? So, but basically this is what we are trying to do. We are trying to come up with a box which we will call as a Rayleigh fading generator. Rayleigh fading generator. Okay. What all do I need to give inputs to this one? I need to give the Doppler frequency. I need to give the sampling frequency. So, what is the spacing between my samples of the fading that I am asking for? And the third one is, what is the length? How many samples? Do I want 100? Do I want 1000 or 10,000? I need to specify, and the output should be ZR of n plus j times Zi of n, which has the correct autocorrelation function that we are interested in. So, the properties that this one should satisfy: expected value of ZR of n whole squared is equal to expected value of Zi of n whole squared should be equal to 1/2. right? So that then together they will give you unit variance as far as the channel response is concerned. The Doppler properties expected, we call this as Z of n, expected value of Z of n, Z star of n plus m, Z star of n plus m. This should satisfy the following property. It should behave like the Bessel function, 2 pi fd, and what else? What else? Delta t, but now it is m, that's all, times t samp. Okay, don't forget that basically m is just an index, but in order to show the extent of the correlation, it has to be a time variable, and therefore the sampling m samples is nothing but m times t samples in seconds. Okay. Now these properties should be satisfied, and we should get a box, and basically Rayleigh Jake's method is one that tells us how to get such a box and how to generate that. Now assuming that you have been able to generate this, what is the next step? The next step is, now basically we are trying to simulate a channel. We say that I want to simulate a channel where the following is the response: Z1 of t, S of t minus tau 1, Z2 of t, S of t minus tau 2, plus Z3 of t, S of t minus tau 3, dot dot dot. Okay. This is the continuous time version. You can write down the discrete time version as Z1 of n, S of n minus tau 1. You have to look at the actual description of the delays, plus Z2 of n, S of n minus tau 2. Let me just put it as bar. Basically you have to quantize it to the appropriately. Z3 of n, S of t minus tau 3 bar. Okay, and goes on. But how do we actually implement this in the, so what you would do is call multiple times the Rayleigh fading simulator, 1, 2, however many you have. This is the nth multipath component. Each of them is generating an independent Rayleigh fading according to the statistics that have been specified. Now each of them has got a different power level. So this multiplicative factor is alpha naught is expected value of mod Z1 squared. Okay, so basically no, it is square root. Okay, so it's an amplitude scaling. So when I take the power level, it will scale to get the corresponding. So this is a unit variance random process generator multiplied by a scaling to get the appropriate power levels, and so on and so forth. You get the corresponding statistics. Okay, so and you take the input signal, multiply it with the corresponding gain for the first term. Second coefficient has a delay tau 1. You multiply it, and then you add all of them to get the received signal. So this particular model is implementing the following process. It has got a tap at 0 delay, which has got a power level of alpha naught squared. Okay, this is in the power delay profile, and then there is a second tap which is at a delay of tau 1, which has got alpha 1 squared as the average power. Then there is a third multipath component which is at a delay of tau 2, which has got alpha 2 squared as the. So this is what this figure is implementing. Each of these are Rayleigh. This is Rayleigh, has got Rayleigh statistics. This has got Rayleigh statistics. This has got Rayleigh statistics, and so you have. So all of your channel impulse responses, each of those coefficients has got a of Rayleigh statistics. Now the question that so once you have a Rayleigh fading generator, you can call multiple instances of them to generate independent or different Rayleigh random variables. And then you multiply it with the appropriate delays, scale it to get the appropriate power levels that you are interested in. So basically this is the power levels that you are interested in, these are the delays, then you combine all of them. So this is what is at the end of the day, what you have obtained is a time varying frequency selective Rayleigh fading channel. Rayleigh fading channel. Okay, so this is what we need in our simulation, and that's what we have been able to obtain. Okay. Now the key question is Rayleigh fading simulator. I know we can do Clark and Gans, method 1. Then there is the Smith method. Then third one is the Jakes method. And the Jakes method is what we are going to be looking at in the next lecture. Again, it's a non-intuitive model. So the way we are going to do it is rather than try to motivate how Jakes came up with it, we will present you the Jakes model and then show that it satisfies the time domain correlation, it satisfies all of the properties needed for Rayleigh fading. But in order to know what those properties are, definitely would recommend that you take a look at the propagation handout that has been given to you. Propagation, Wiley propagation handout, and that will tell you the model and also tells you what are the basic properties of the Jakes model, so that you can then appreciate it when we discuss it in the class. So there is a handout which has been uploaded in Moodle, you can take a look at it, and that talks about the Jakes model. It's a non-intuitive model, but it's a beautiful model because it satisfies all of the requirements of the Rayleigh fading statistics, basically all of the properties that we are interested in, and satisfies them in a very, very nice manner, very compact manner. And today, almost all researchers in wireless who work with fading channels, particularly Rayleigh fading channels, would be working with the Jakes model. So one of the things that we will do in the next computer assignment is actually have you program the Jakes model and make sure that you are able to verify the statistics that are obtained through the Jakes model. Okay? We will pick it up there in tomorrow's class. Thank you very much.